who happens to be from the same place where I studied, although displaced in time by 10 years. So Delhi University is the place, and he did his master's and PhD at University of Delhi, and then he has been at the SNBCBS Center since many years, and he's now the head of the department and a senior professor there. As far as his research interests go, of course, I can go on and on, but just to summarize it briefly, he comes from the field of cosmoparticle physics to doing interesting problems in quantum information theory, and his interests are very diverse. So I would put him in the category of broadband physicist, whom you can go and consult on problems of various kind, including mathematics and probably also computation related, now that quantum information is very much coming up as a interesting hot topic. His areas of interest are in general quantum information and foundations, and general relativity and cosmology. And his publications range from all physical review A to D, I would say, and in also cosmology and general theory of relativity and so on and so forth. So without taking more time, Professor Majumdar, please.
Yeah, thank you, Professor Mehta, for such a kind introduction, and thank you so much. And I'm really, it's heartening to know that we share the same alma mater. And
yes.
Although, as you said, rightly separated in time, but still we have nice memories of our universe. Right. So thank you so much. And before beginning, I would like to request you to please remind me before 5 minutes, before the 5 minutes before the end of my talk.
Sure, so, I will do that. Yeah.
And let me also thank the organizers formally once again for arranging this beautiful, month-long meeting, and especially this workshop, 7-day focus workshop on quantum information and communication. And we have had the pleasure of listening to so many wonderful talks by leading experts from around the world and also young researchers in the country. So today what I'm going to speak of is certification of quantum states and devices. And because as I see there are a lot of young students in this audience, so my focus will be to convey some message, and we may not necessarily be able to discuss all that I have in the slides, but please feel free to interrupt me or ask questions or raise hand at any point in the talk. So that is the whole purpose, to get some ideas or messages across to you. So this is some area which we have been working at the SNBCBS National Center for Basic Sciences over the last 3 or 4 years, or maybe slightly more, along with our group of students, ex-students, ex-PDRAs. For example, Jevaratnam was a former postdoc, now is in Europe. Devarshi was also a former postdoc. He's got a Newton Cambridge Fellowship. He's got there now. Devashish Shah is an existing NPDA, but he's got an offer in Iceland. Trivandrum, Shiladitya Mal is also present in abroad, same as Shuchetana. Bihalan has just completed his PhD thesis, and so similarly Shorodip and Anando has just had his defense. So these are the theory collaborators, and we have also some experimental collaborators from China, mainly led by the group of Peng Qiu and Zihao Bihan. So the whole point of today's talks is that by now many of young students are aware that aware of the importance or significance of quantum information science and the utility of quantum states.
Professor Majumdar, sorry to interrupt. Could you please make it full screen? Your slides are not coming full screen.
Okay, from my side, it is full screen.
It's not
so
showing.
Should I exit and try to?
Probably,
maybe I should.
Yeah. Yes.
I should exit and try to share once again.
Yes.
Yeah, please. So now is it okay? Is it?
Yes. Now it can.
Okay, sorry for the error. Thank you so much. Yeah, thank you so much. And so as I was saying that, I mean, young students by now must be aware that this is indeed, I mean, a field for the future with promises of so many new kinds of technology. And in that endeavor, actually, quantum states and devices play a major role. And of course, as with any kind of devices and any kind of prepared states, one needs to be sure that they do have certain properties which we would like to have. For example, an experimenter who would like to implement some quantum information protocol, like say teleportation, dense coding, or secret key sharing in the laboratory, needs to be sure that he or she has access to, I mean, entangled quantum states, and more likely maximally entangled quantum states. And also the devices by which he or she perform measurements of those states are also working in the way that we expect them to work. So how can we be sure that that is indeed the case? Because as you know, in other words, there can be manufacturing devices, manufacturing errors in the devices which are supplied to you by some supplier. And similarly, when somebody prepares a quantum state is an extremely fragile object, and it can actually interact with the environment and decoherence can occur. And also there may be some parties with malified intentions who can play a spoiler by spoiling the entanglement of quantum states. So how could we ensure that what we are receiving in our hands, that like quantum states and devices, are actually what we want them to be? So that is the whole endeavor, and this plays a very important role in any kind of quantum information processing. So the plan of this talk is as follows. So first of all, I would like to share with you, I mean, why, as I said now, I mean, in a more formal way, what is meant by certification of quantum states and devices. And even more particularly, there is a nice name which is given to this endeavor, which is called self-testing. And self-testing is something by which we could certify quantum states and devices with minimal possible assumptions about anything, about the supplier of the devices or the supplier of the state. So I would spend some minutes in motivating this, and then we would move into what we can really do using such self-testing. And the first program that we implement is one-sided device-independent self-testing. And I would make clear as we go on what we mean by one-sided device-independent or semi-device-independent self-testing, as different from fully device-independent protocols. And such protocols are actually depend on a very beautiful formulation in quantum mechanics that was thought of way back in 1935 and 36 by Erwin Schrödinger, and that is called quantum steering. So this was in response to the EPR paper, for those of you who are aware. So this is the theoretical background for such kind of implementation. Then we would spend some time in discussing the first experimental implementation of this one-sided device-independent self-testing scheme, which was done in collaboration with our Chinese colleagues. And in the last part of the talk, depending on how much time is available, I would move to another way of doing self-testing that is not based on spatial correlations that you are so familiar with, like the correlations that violate Bell's CHSH inequalities, but on the other hand, which are based on temporal correlation. So I will discuss that, and I will also discuss, time permitting, how we can self-test devices that perform Pauli spin measurements and later on even arbitrary outcome measurements. So that is the plan of this talk. Okay. So as I said, what is basically self-testing? Self-testing is a form of certification of quantum states and devices. So if we can verify quantum states and devices without having direct access to the quantum system, so that is the whole idea of self-testing. And when can we not have direct access to quantum states and measurements? When these states are, say, supplied by a third party, and for example, the measurement devices are manufactured by someone else, the manufacturer. So the whole idea here is to actually certify quantum entanglement without access to quantum devices, or in other words, without trust of quantum devices. So that is the name of the game, that even if we do not trust the supplier to supply us with ideal quantum devices, even in that case, can we certify, can we say that indeed such quantum devices perform exactly as we want them to perform. So pictorially, or in a way of a cartoon, suppose you consider two parties, say Alice and Bob, and they share a state between them. So for example, somebody has prepared an entangled state or a pair. One of the particles goes to Alice and the other goes to Bob. And Alice and Bob are indeed spatially separate. So now here do we come in, Charlie or the third party or us who are actually certifying, or what we want to do, the third party wants to actually certify or verify that Alice and Bob indeed share an entangled state. Okay, but the third party doesn't have direct access to either the state or to the measurement devices employed by Alice and Bob. So that is the key. So how does the third party or Charlie go about it? Well, Charlie has to ask some questions from both Alice and Bob. And if we label these questions by small x and small y, small x to Alice and small y to Bob, which form a part of a set of questions labeled by capital X and capital Y, and Charlie receives answers from both Alice and Bob, which are labeled by A and B, small a and b, and these answers could also form a part of a set of answers labeled by capital A and capital B. So depending on the questions asked and the answers supplied by Alice and Bob, if Charlie is able to certify or verify that Alice and Bob indeed share a quantum state, an entangled quantum state, then we are successful in this task of self-test. So how is it accomplished in practice? So of course, Alice and Bob have to be given a definite strategy, and this strategy actually determines a collection of probability distributions of the answers of the given questions. And such probability distributions are conditional probability distributions in the sense that suppose Alice and Bob perform measurements which I labeled as questions given by X and Y, and Alice and Bob get outcomes given by small a and small b respectively, then one could define a conditional probability of getting outcomes A and B conditioned on performing measurements given by X and Y. And the collection of all such possible measurements and outcomes define for you a conditional probability distribution. Okay. And what do we refer to? What do we state? We say that actually such probability distributions define nothing but a correlation. Okay. Because correlation of what? Because Alice and Bob are sharing an entangled state. That is what we want them to do. And such probabilities actually define for you exactly what is the correlation. And we call the strategy quantum if it can be obtained by some quantum strategy, right? From using some quantum states and measurements. So what specifies a quantum strategy? So for example, if you have a joint state, bipartite state shared by Alice and Bob, and to begin with, let us assume that both of them perform projective measurements, although the argument is more general, they can perform other measurements as well. And these are represented by these projection operators. So such a probability is defined by nothing but the expectation value of these projection operators on the state side, right? And you can actually get all these outcomes and form with you and keep with you a set of these probability distributions. Now, what do we do now? So for example, the aim here, as I said, to repeat, is to certify the behavior of quantum states, quantum systems, both states and devices, based only on these observed correlations or these probability distributions. Now, in order to play this game, Alice and Bob must make some assumptions at least. And if you have fully device independent self-testing, the only assumption that they need is that Alice and Bob obey quantum mechanics. And of course, there is the no signaling constraint. That is, there is no exchange of messages. There is no signaling either way between Alice and Bob. So these are the minimal assumptions that Alice and Bob have to obey. Now, let us come to the formal definition of self-testing. So what is it? So we have already defined for you a correlation. And we say that a correlation actually self-tests a state which is labeled as psi target if that is psi target can be uniquely achieved when Alice and Bob make local measurements on psi. But it has to be up to some local isometers. So for instance, what are we saying? We are saying that Alice and Bob have a shared quantum state psi, and then they are allowed to make actually local measurements on psi. The Alice makes measurement on her part of psi, that is her particle. Bob makes measurement on his particle. And then if we get some correlation out of the collected probabilities, then we say that a correlation is able to self-test a state which is psi target. Okay. up to some local isometry. So that is very important because we can never, self-test the state uniquely because each site is allowed to make some unitary operations, and that are labeled by local isometry. So it will be clear when we move on, right? So let me give you an example. Suppose we want to self-test a maximally entangled pure state. So we ask questions X and Y from this set 0 and 1, and we get answers -1 and 1. Okay. So for example, it is a spin pair, an EPR correlated state. We want it to be that, and Alice and Bob are performing measurements on some spin-off measurements along some chosen axis, and all they will get is either upspin or downspin, labeled by -1 and 1. So then we know that in this case, we can write down the Bell CHSH correlation, and the expectation value of this Bell CHSH operator will achieve the maximum possible value of 2√2. Okay, in quantum mechanics, you can never go beyond 2√2. Of course, all of you know that in classical theory, the maximum limit is given by 2, and Bell's inequality tells us that if we assume local realism, then this number will be less than 2. However, in quantum theory, this is called the Tyrrellson bound, 2√2. So if you are able to actually achieve this 2√2 by using such correlations upon performing such measurements, then we say that such correlations actually self-test. So in other words, the correlations in the quantum correlation set that achieve this maximum violation self-test the maximally entangled pair of qubits. So that is what it is. An old result by Popescu and Rodlik in 1990. So this seems to be extremely simple. Okay. So now let us move on. So suppose instead of maximally entangled state, suppose we have some imperfections and the state is not, then how do we go about it? So instead of the original CHSH inequality, we use here another form, which is called the tilted CHSH inequality, which is labeled by this parameter alpha. So this is the only difference. And now what does the CHSH tilted inequality tell us? That this bound, the local realistic bound, has to be less than or equal to 2 plus alpha. Now, maximum violation in quantum mechanics of this is given by root of 8 plus 2 alpha square. And also, the maximum quantum violation self-tests the tilted EPR pair for this state, say psi theta. This is the non-maximally entangled state, labeled by this parameter theta. So, for example, if both of them are equal to 1 by root 2, that is theta equal to 45 degrees, then it reduces to a maximally entangled state. However, if for any other value of theta, we see that the maximum, whenever the maximum violation is achieved, we can say that indeed Charlie or the third party is able to satisfy himself that Alice and Bob are indeed sharing this state, okay, this non-maximally entangled state. So these results were also known. So this was by Archan, Masar, and Pironio in 2012. Okay, so what has been the progress of this kind of device-independent self-testing so far in a nutshell? So first of all, it was achieved for maximally entangled qubits by Mayers and Yao in 2004, who proposed the first formal, theory or proof of self-testing. And as you now, by now, you should appreciate this is extremely important in practical information processing. And so the next question arose is that, as we would come into that again, how can you say that in an experiment you can achieve maximal violation? Because you see, all of these were based on maximum violation of these inequalities. Now, any experimenter would actually challenge me at this stage and say that in a real experiment, it is extremely difficult to actually achieve this maximum violation. There will always be certain efficiencies, detection efficiencies, signal loss, so on and so forth. So in practice, you end up with achieving not perfect, not the full quantum correlation, but a small subset of it. Okay, some bound, some magnitude lesser than 2 root. In that case, should we back up and forget it? No, but these people actually, Scarani et al. Showed in 2012 that even if we achieve a lesser magnitude of Bell violation, we can still say that self-testing is possible, and that was the theory of robust self-testing was first proposed by them for a single state. Okay. So then we move on. In 2015, these people, Bams and Pironio, showed that not just maximally entangled state, but all pure entangled qubits could be self-tested. Then later on, it was extended to maximally entangled Q traits. I mean, if you increase the dimension of the Hilbert space. In another direction, if you have more number of parties, that is n singlets, you can also achieve self-testing. And finally, the group of Scarani showed us 3 or 4 years ago that you can do this self-testing for all pure bipartite entangles, right? So this is a nice story of development. So now you can ask me, from where do we go from here? Of course, so those of you who are still skeptical about self-testing, so I'll just give you a flash slide, again highlighting the importance of self-testing. Many applications have been proposed. So for example, one could test Hilbert space dimensions of a given system using this method of self-testing. Then those of you who are interested in secret key sharing, so this is a very big industry, quantum cryptography nowadays. So practically we have cryptographic devices which are available in the market. So you can ask me that, can you be sure that you are performing device-independent quantum key distribution? And the way to do it is again through self-testing, as was proposed by Miller and Shi in this way. The other thing which is very important is to generate random numbers in cryptographic applications. And again, you can be sure that the randomness generated is indeed quantum random numbers by the method of self-testing. And then the next thing which is going to come up once we indeed have quantum computers, as all of you know, it may be very difficult to build at a single place very large quantum computers, by that mean a large collection of qubits at a single place. But you could also do with collection of qubits, locate small number of qubits, located at different places, but connected through quantum networks. And that is the name of the game called delegated quantum computation. And even here, if you want to test that the network is performing fine, again, the answer or the method is to apply self-testing. In fact, as I said, this list is by no means exhaustive. There are numerous other applications. So in fact, I would say that any experiment which is based on using pure state entanglement can be verified or can be achieved or can be trusted by the method of self-testing, right? So this was a major kind of introduction about this area. So now, where do we come in? So we entered this area not from fully device independent self-testing, but from semi-device independent self-testing. So now you can ask the question, why semi-independent, semi-device independent self-testing? Because as I showed you in the earlier slide, a lot of people have indeed achieved fully device independent self-testing, not only in theory, but there have been experiments as well. But the major point here is that if you want to do fully device independent self-testing, it becomes extremely hard to implement in practical situations. Why? Because this is based on maximum violation of the Bell CHSH inequality. And any experimenter would immediately tell me how hard this experiment is, even for a pair of particles. Okay. So that is difficult to achieve, and it requires detection efficiency, which are more than 80–85%. So that is a hard problem to implement in practice. But on the other hand, what we have in many different applications, that in many number of cases, partial knowledge or trust of the devices is available. Okay. So in many realistic situations, what you can do is you know that at least you have knowledge or trust of a part of the system, realistic situation. So in such kind of situation, it is indeed possible to relax some conditions that are required for implementing the fully device-independent protocols, which are extremely hard to do in practice. And these protocols can be self-tested, robustly self-tested, and such a theory can be constructed with lesser resources. So that is the whole idea in quantum information processing. Resources, preparation of resources and utilization of resources are extremely expensive. I mean, expensive. So there is a whole resource theory behind that. You indeed have to generate entangled states, and then you have to generate fully functional quantum devices. So that is extremely resource consuming. But semi-device independent or one-sided device independent self-testing requires a much lesser magnitude or much lesser quantum of resources. So that is the motivation. And as I said, to continue with the motivation, we stick to one-sided device independent self-testing. And this I should repeat because this is very important. As I was saying, that in many realistic situations, one of the parties can be trusted while the other is completely untrusted. And you can easily imagine if you have a server-client relationship, for example, there is a bank and there are many clients, okay? So then you can actually, the bank server is trusted, whereas the clients may not be trusted. Similarly, if you have a manufacturer of quantum devices, the device with the manufacturer may not be trusted, but once you get the device and you can connect with the manufacturer, you can actually trust your part of the device, okay? And so if you have, as I was saying earlier, so if you have an entangled state produced by a third party, the part that you get is trusted, whereas the other part may not be trusted. And this list runs on, so on and so forth. So this is also extremely useful for the practical point of view. So to repeat once again, what are the advantages of one-sided device-independent self-testing over fully DIST? That this protocol of one-sided device-independent self-testing is based on quantum steering, which was in fact indeed suggested in 1936, that is almost 30 years before Bell inequalities by Bell. And quantum steering-based protocols indeed require lesser resources, okay? And indeed, since you have one of the sides is well in your control, so there, as you can imagine, there is less sensitivity to decoherence effects and better error tolerance. And not only that, even if you consider detector efficiency, so a 50% efficient photon detector, for example, can implement quantum steering, whereas for the same case, you need 83% for Bell violation to close detection loopholes. So those of you who are aware of this game know that there are several loopholes in these experiments called locality loophole, detection loopholes, etc. And a much lesser efficiency is what is needed to implement quantum steering. And there are other examples and technical benefits also. Okay, so what is this one-sided device-independent self-testing? It is based on quantum steering. So what is quantum steering? So suppose there is a source here which manufactures a pair of entangled particles, and one of the particles goes to Alice, whom we do not trust, but the other goes to Bob, who we trust. So suppose Bob is the client who we trust, but this side is the provider. So we neither trust the source nor trust Alice, what Alice does. So in this case, how can we implement steerability? Well, mathematically speaking, again, we come to probabilities which we defined in our earlier slides. So PB, PAB given XY. XY are the measurements performed by Alice and Bob respectively, and A and B are the outcomes. And suppose if that probability cannot be written as a sum of this thing where these P's are individuals. Okay, so Alice can perform a measurement that Alice's measurement is completely unknown or untrusted. So this is represented by a black box, and the outcome is given by here A. And of course, we can say that Alice measurements are contingent on some given variables here lambda. And similarly, on the other side, we trust that Bob indeed has a quantum device. So we say that Bob has some kind of a quantum state, which we don't know, which is given by the given state rho lambda. And Bob's outcome are given by B. Okay. And Bob performs a measurement in the Y direction, for example. So if the probability cannot be expressed like this, then we say that steering is implemented. So how can we actually implement, how can we actually write down, mathematically represent Alice's unknown measurements, because we don't know anything about Alice's measurements. So such measurements can be labeled in terms of POVMs, positive operator valued measures. So this is a collection of positive operator valued measures. So each one is represented by MA given X. X is the sum label of the measurement, A is the outcome, and collection over all A and X represent this set. And by definition, we need to have this positive, and also so the sum of them should add up to 1. So now when Alice performed this measurement on the shared state, we say, because the state is entangled, we say that contingent on Alice's performing such measurements, and assemblage is produced at Bob's sides, And what is the assemblage? It is just a collection of such conditional states. So these are unnormalized at the moment. And what are these conditional states? Sigma A given X. These are just represented by the probability of occurrence of outcome A, given X measurement is performed by Alice, and then this rho A of X is the state on the other side. This is pure state by. Okay. And we can obtain this assemblage exactly by this relation. That is, take the POVMs, measurement operators, and then actually apply this on the foot state, rho AB. Okay, tensor identity. Right. And this condition of steerability can also be expressed in terms of these assemblages, that is sigma A given X, whenever it cannot be expressed as a sum of the probabilities P lambda, this is the probability distribution of hidden variables, and the probability of obtaining outcome A given X lambda, rho lambda. Okay. So what does it mean? That if you cannot express this in this form of this sum, then you can say that there exists no local hidden state model for Bob assembly. Or in other words, Alice, through her act of measurement, is indeed able to share Bob's state or Bob's particle, which is located at some distance away from Alice. So this is the meaning of quantum steering. Okay. But now, how is it relevant to self-testing? Okay. But before we go to that, so this was definition of steering, but can we say something more quantitative? In order to do that, one could define some measures of steering. So these measures will also be required in our subsequent discussion of self-testing. So let me go through it very quickly. If somebody has a question, they can ask me later. So what one does is to define such measures using a decomposition of this assemblage in terms of the steerable assemblage represented by sigma S and the unsteerable assemblage represented by sigma unsteerable. And this is a convex decomposition. And the weight or the quantifier of steering, called the steerability weight, is just given by this PS, which is minimized over all possible decomposition. So this was definition was given by Leggett-Garg et al. In a PRL paper 2014. But as you see, this decomposition, this definition is based on assemblages which are not physically measurable quantities. So some years ago, we thought that let us propose another definition which is given by probabilities which are indeed physically measured, physical objects. So we came up with another decomposition and another steerability measure, which we label as steering cost. Anyway, so let us now move to our original purpose. What do we mean by steering? So now we want to implement one-sided device-independent self-testing. And for a pure state, for a maximally entangled pure state, this task was already defined by Suppi-Koban et al. In these two papers, 2016 and 2017. So what they consider is to actually certify a pure entangled target state, which resides in this Hilbert space, this tensor product Hilbert state H prime at Alice's side, tensor HB at Bob's side. And their task is to actually certify it from a steerable assemblage, as I was discussing, which arises from this state, psi A. So psi twiddle is the target state, and psi AB is the actual state, which is indeed shared by Alice and Bob. And they perform measurement operations labeled by M on Alice's side. So what are the conditions for self-testing? So the conditions or assumptions are as follows. So we can allow operations on Alice's side which leave the physical assemblage on Bob's side, right? So that is what I actually said by meaning that local unitaries or up to local operations self-testing is performed. So in other words, we can define an isometry on Alice's side, which takes a state, if we act this isometry by this operator phi, so it takes a state from psi A Hilbert space into psi A tensor H psi A prime, such that these conditions are obeyed. So in a nutshell, what is the physical meaning? So I can allow Alice to perform as many local unitary operations as possible. And this also actually includes embedding his part of the state into a larger Hilbert space by taking a junk state and embedding the state together here, and also performing all kinds of local operations, unitary operations or measurements as possible on Alice's system, which is combined, which is given in a combination of the original part of the EPR state as well as the junk state. So you can see that from here, self-testing is possible only up to local isometry. So this is the name of the game. And then we came up with the proof of self-testing for not only maximally entangled state, but any non-maximally entangled pure state of qubits, which is defined by this parameters theta, right? So here is a generic non-maximally entangled pure state for 2 qubits. And what do we say? That Bob measurements let us take in maximally unbiased bases, MUBs, which are given by this, V0 and V1. And let us, to begin with, say that we don't know what Alice performs, but we have to start with some kind of ansatz. So let us say that Alice's measurements are given by this A0 and A1 defined like here. And now what we employ here is, instead of Bell-CHS inequality, a steering inequality, which is called the fine-grained steering inequality, which was also presented, or actually which was devised by our group some years ago. So this is called the fine-grained steering inequality. And if you use the steering inequality in order to achieve self-testing, then as we can say, as we proved in this work, that maximum violation, that is, if you have the LHS, that is the sum of these two probabilities, condition probabilities, if you have them exactly equal to 2, this probability is only possible for these measurements and up to locally. So the whole point here is that if I can make any other kind of measurements on this particular state, then maximum violation of this inequality is not possible. So maximum violation, that will lead me to 2. That is, individually these probabilities will be equal to 1. Only if and only if I perform these particular measurements on this particular state. So that is the proof. So I will not go to the mathematical details of the proof. So if you are interested, you can ask me, and here again we use this quantifier of steering and we get it. So let me skip this mathematical discussion of the proof. Now let me come to something more interesting. So we can say that indeed by performing such measurements, Alice and Bob, or a third party, is able to certify that Alice and Bob are indeed sharing a pure 2-qubit entangled state. So that state is self-tested using minimal assumptions. But can we do further? Can we do a little bit better? In other words, can we ask which exact state are they self-testing, or how much entanglement are they certifying? Okay, and the answer is again yes, as we showed in this work, and this state identification is possible by 2 strategies. Now, as you saw from the state, there is nothing very special about the state. So this is just a 1 parameter. And also this is true for up to local isometries. That means you can take this triplet form to other 2 possible triplet forms, and also to singlet form. By that I mean, instead of 0, 0 plus 1, 1, I could also have 0, 1 minus 1, 0, or 0, 1 plus 1, so on and so forth. So, but the whole point is given by theta. So theta here is the parameter, and in other words, can be identified through our measurement without having access to the state or without trusting Alice's device. Can we say what is the value of theta? The answer is yes, and we can define it in 2 possible ways. One is through concurrence and violation of this other steering inequality. So these are monotonically related. So once we know these things, we can certify which state we are identifying. And the strategy 2 is through employing another quantity which is called mutual predictability. Okay, so we can do it. So now let us come to the question of robustness of self-testing. Why this is extremely important from the practical point of view. Because as I have emphasized earlier also, experimental detection of maximum violation is indeed very difficult. Okay. So usually what we obtain in the laboratory is a certain magnitude of violation. For example, as I said that, if I go back a few slides earlier, what I said with a lot of emphasis that if and only if the probabilities add up to 2, we can state for sure that these measurements are perfectly set. But again, in the laboratory, no probability will be exactly equal to 1. You will always have errors, right? So what can we do? So that is what we mean by robustness. Usually a certain degree or magnitude of violation detected. So can we still achieve self-testing in practice? The answer is yes. And what do we do here? We define a theory of robustness, right? So again, we don't actually first propose it. There were earlier proposals. So we actually adopt this proposal in the context of our work. And this is given by extractability relations. So again, what is robustness? Robustness is defined by lowest extractability when a certain fine-grained steering inequality that we showed earlier is violated. Now remember what we are saying here. This is the most important part. We are saying that FGSI has to be just violated. we don't require maximal violation, right? And we then therefore we actually define this parameter Q. Again, I'm not going into the details of the mathematics. If anybody is interested, I could explain it later. So this form of this expression is defined as follows. And as you can see on the right hand side, there are several functions, and S is the fine-grained steering inequality sum, and SLHS, a lot of you also know, this is the local heating state bound. And in combination of that, and what is A? A is the state parameter, exactly what I was earlier labeling as theta. So this is the state parameter for the non-maximally entangled. Now, using this idea of robustness, actually such an experiment was performed by the Chinese group with our collaboration, and which was the first experiment in the world which implemented one-sided device-independent self-testing for any pure non-maximally or maximally entangled state of 2 qubits. So this was done using a linear optical setup. So these are two sides, Alice and Bob, we say. This is a source laser beam, which manufacturer we sent to them a pair of entangled photons. One photon comes here, the other to Alice, the other goes to Bob. And we do not trust the measurement device of Alice, but we do indeed trust the measurement device of Bob. The idea is to steer Bob's state by Alice, and then depending upon the counts obtained by various detectors, there are 4 detectors in the setup. We actually say that such states can be self-tested. And what was the protocol here? The protocol works as follows. First of all, a joint state is prepared, and then we know, because we know that we trust or we have access to Bob's device, we know that we say that Bob performs 2 measurements, one sigma z, the other sigma x, Pauli spin measurements in z and x directions. But for Bob, we let it be arbitrary. Let Bob choose any particular measurement, A0 and A1, and then depending on the outcomes, we calculate these conditional probabilities. So if we get this probability to be equal to 2, then we exit this loop and we go toward this side. But suppose we do not get this 2, we send it back again to here. Bob repeats his same measurement settings, but Alice chooses a different pair of measurements until and unless we get it to be equal to 2 or within experimental accuracy near to 2. So if we get back, then if we get near about 2 value, then the answer is yes. Then we move to the right hand side. Then we call these 2 functions, which are again functions of the correlations. And using these correlations, there are again 2 methods from which we can determine. So in the end, we end up having exactly determined the state which was given to Alice and Bob. That is, if the state is 5 plus or 5 minus any possible Bell state in the 4 Bell states. And also, not only that, we are able to exactly determine what Alice's measurement setting are. Right. So indeed, we end up self-testing this state and measurement device. So these are the experimental results. Again, I won't spend too much in technically discussing them, but just the idea of robustness that I told you. So what happens is that, as I said, the probability is never equal to 2, but we end up with a value of probability which is less than equal to 2. But what we have to satisfy experimentally is that indeed this Q function, which I determined earlier. So in this 2D plot, the Q function contour is plotted like this versus 2 parameters. See, on the x-axis is the parameter A, that is the state parameter, and on the y-axis is the violation of the fine-grained steering inequality. So whenever we get experimental detection which are labeled by these crosses, which lie above the contour of this robustness function, we can say for certain that our scheme is indeed robust. In other words, even with lesser magnitude, not non-maximal magnitude of violation, we are able to certify with certainty what the state is. The state is entangled, and also we are able to determine what the state is. Okay. Again, let me not, because I am coming toward the end of my time, let me go on to the last part of the talk, that is certification of measurement devices without using entanglement. So this I need not repeat that generating and preserving entangled state is extremely difficult in practice. So now we ask the question, can we self-test measurement devices without using entangled states? Okay, so that is the question we answer, and indeed we say that yes. And what is the method? we adopt here, we say that we, instead of using entangled states, we say use single qubit states and perform measurements at 2 instants of time. And these 2 measurements that perform, I mean, one at time t1, the other at time t2. But again, if we define correlations in these measurements, they are, if the measurements are quantum and the state is quantum, then we find that there exists certain temporal quantum correlations. And using temporal quantum correlations, we are able to certify measurement devices. So this is the statement, is the content of this paper, which was published in 2021. So what is the setup? The setup is here that we send, say, an input state, which can be anything, single qubit, 2 qubit, separable, whatever we have, it is a quantum state, to some party which is called Alice. And Alice's measurement device is oriented along a certain direction, which we labeled by AI. And Alice's outcomes is labeled by small AI. And then after the measurement, the state is passed on to Bob. And similarly, Bob performs another measurements, and we take correlation. So these are 2-time correlations, again labeled in the same form, but these are not CHSH spatial correlations, but these are temporal correlations. Now, we can construct such correlation functions labeled by Cij using these probabilities as defined as follows. These are conditional probabilities. And using these Cijs, we can define a sum in various possible ways. And here is a possible sum, C11 plus C21 plus C22 minus C12. And this was actually, this particular combination was defined not by us, but now more than 30 years ago by Leggett and Garg. So they called it as Leggett-Garg inequalities. And in this context, these are nothing but temporal quantum correlation inequalities. So if we assume that we are not doing quantum mechanics, but we are having a macroscopic realistic picture or a classical realist picture of the world, then the sum of these 4 terms can never exceed 2, right? So the upper bound is 2. And whenever this Leggett-Garg inequality is violated, then we say that whatever we are doing, the state is quantum and we are implementing quantum operation. Okay. So this is the motivation. Entanglement is a costly and fragile resource. Qubit systems are the one which are most widely used in QIP. So can we devise a protocol for self-testing binary Pauli measurements without entanglement? And indeed we do it based on temporal correlations, that is violation of the Leggett-Garg inequalities. Okay. So how are Leggett-Garg inequalities defined? So just for people who do not know, so how can we define classical realism? This is a combination of 2 assumptions. One is non-invasive measurement and the other is realism or macroscopic realism. And there is also another form by which we can actually define the mathematical form of Leggett-Garg inequalities. And that is these 2 statements. One is called predictability, that is the joint statistics, this 2-time statistics that we have defined. It can be 2-time, 3-time, whatever time, but if these probabilities lie within this interval 0 and 1 for all possible measurement settings and all possible outcomes, then such a thing is called as predictability. And the next idea is to do with no signaling in time. And what does it mean? That suppose Bob performs a measurement Bj, okay, and if Bob's measurement is given by this, that is a condition probability of Bob performing a measurement, whereas Alice has performed any kind of AI at any earlier instant, it is not dependent on Alice's measurement, then we say that there is no signaling in time. In other words, by performing a measurement first by Alice, it won't affect or impact Bob measurements outcome performed at a later time. Okay. So in other words, measurement statistics, when they are not influenced by earlier measurements, we call such a situation no signaling in time. And if we take 2 of them together, that is no signaling in time with mathematical notation with predictability, then we get LGI. And whenever LGI is violated, it will tell you that one of them is violated. And so indeed we are in the quantum regime. Okay. So again, we implement the same kind of self-testing, which the argument is familiar to you. We take a state, we start with the state, and we perform qubit measurements. And the self-testing arguments thus follows. Whenever maximum quantum violation of this K4, which is defined like this, is achieved, we can say with certainty that ideally Alice and Bob are performing such qubit measurements. Alice along Z direction, and the two possible measurements of Alice's settings are A along Z and X direction respectively, whereas Bob is performing this combination, right? So this is the magic. If Alice can do anything and Bob can do anything, but whenever such a condition is achieved that some of these correlations is equal to 2√2, then we can say with certainty that Alice and Bob are performing indeed such binary Pauli spin measurements using quantum devices, right? And also we can implement robustness. As I said again, the sum need not be exactly equal to 2√2 in practice, but whenever this function, that is this f function, fidelity function, exceeds the lower bound, which is represented by this red line, and this fidelity function, for instance, we can consider the effects of various kinds of noise. Suppose we have a general dephasing channel, then the correlation function will never be exactly equal to 2, but we will have a lower magnitude. But whenever the correlation function, which is the average fidelity, for example, for the dephasing represented by the blue line, lies above the red line, then we can be sure that we are indeed certifying the measurement devices with certainty. So this is the name of the game. And now the question is, now again, somebody can ask a question that who tells you that the state is two-dimensional, right? So we are indeed performing binary spin measurement of all the devices, but in this game, we cannot be sure. We cannot define for you what the state is, because the state is prepared by somebody else. Okay, so the answer again we supply here that there is indeed no dimensional restriction on the input state. The state can reside in any possible direction, but still we are able to achieve this state. So in the last couple of minutes, so earlier work we talked about binary outcome measurement, but suppose we don't confine ourselves to Pauli spin measurements, but if we consider arbitrary outcome measurements, right? Because the state can be anything, so it can be a QIQT measurement or any D outcome measurement. Can we still certify our measurement device, number one, and can such certification be done without entanglement? And the answer is again yes, again based on violation of temporal correlation-based inequalities and a minimal set of assumptions. So this is the work which was done with Devashish and Anando and Devarshi, and which got published just now in this journal Quantum just a few weeks ago. Okay, so here also the game is as follows. So here we have a single measurement device which is called by Alice. So some supplier supplies you some state we do not know, and Alice performs arbitrary outcome measurements and keeps sending back. This is a loop. So this loop runs for 4 times. And then Alice performs measurements at 4 different instances of time, and then we again define our correlation, and using that we certify it. So we have to indeed make some measurements indeed. And what are the measurements that we have to make? To begin with, the preparation device has to prepare maximally mixed states. Okay, represented by this 1 by identity 1 by D, identity by D in D dimension. So where D is arbitrary. Now you can ask me that how can we ensure that this is indeed a maximally mixed state, but the answer is in fact trivial. So whatever state experimenter or somebody supplies you, if you let it just lying around in the environment for a certain time, it will end up to a maximally entangled state. Okay, there will be no correlation, nothing, no coherence left. So this is just a technical assumption. It is very simple to achieve in practice. And the other assumption that we have to make is that the measurement device that we have here has 2 memory. Okay. So for example, when I is equal to 2, the second time Alice actually performs a measurement on the state, the recycling state, Alice remembers, or the measurement device of Alice has no memory of the earlier state, right? So again, we perform the same analysis. In the case, the structure of the temporal inequality has been worked upon. So this is not just a simple Leggett-Garg type of inequality, but this is obtained in terms of sum of squares decompositions, not indirectly in terms of the conditional probabilities. but in terms of the Fourier transforms of conditional probabilities. And we actually adopt a similar procedure for certification of quantum measurements and also robustness analysis. Everything can be shown. But we do not end here. We also perform an application of this kind of self-testing, and this is indeed in randomness certification. As many of you know, to certify quantum randomness, it's extremely important in quantum distribution. So so given you a set of random numbers, so you have to show that you have to satisfy yourself that in order to implement QKD, that these random numbers are not just coming to you from any classical strategy, but from some quantum strategy. And again, our protocol of self-testing helps in this matter. We are able to show that using these violation of temporal correlations based self-testing, we are able to implement quantum randomness generation. So finally, this is the end. This is the last slide, and this is the summary slide. Self-testing, the message I want to convey to you. Self-testing can be done in two ways. One of them, as I showed you, through entanglement, and the theory that we have worked on actually identifies any pure state and measurements to the maximum violation of fine-grained steering inequality. We have shown how robustness analysis can be achieved even in practice without obtaining this maximum violation. We are able to self-test. And to repeat once again, this is a lot more advantageous compared to fully device independent self-testing. It requires less detector efficiency. And the experiment was performed by the Chinese group. Now, the second kind of self-testing, that is self-testing of quantum devices, this can be achieved without using entanglement, as we showed in these two papers. First, in the context of binary spin measurements, and secondly, we did it for arbitrary outcome quantum measurements, again based on temporal steering inequalities. Right. So thank you very much, and thank you so much for your patience. Now I would like to welcome the questions.
Yeah. Thank you very much, Professor Majumdar, for finishing almost on time. I didn't have to remind you as well. So now the floor is open for questions. I see one question in the chat box by Devdutt Sharma. If you would like to unmute and ask, you could do so, or I can read the question as well.
Yeah, I can also read it actually. Yeah. So the question is, how can we reversible computing as minimize resources? Sorry, maybe it was typed in hurry. Because, so can the questioner unmute?
Participant, can you please unmute yourself, Devdutt? I see him logged in.
Hello?
Yeah, please.
Hello?
Yeah, we can hear you. Yes, please, go ahead.
Yes. Sir, we also use the reversible computing as a resource minimization. Reversible computing.
No, I don't know what exactly you mean. I mean, reversible computing, I mean, how is it related to what I discussed in this lecture?
Yeah.
Because we already use reversible computing as minimum source resource or minimum energy also. Then can we use this type of computing in this domain?
So sorry, can you repeat it? So can we use?
A reversible computing means a reversible gate. We can use reversible gate in order to minimize our resource also. Optimum use of resources.
Okay.
Reversible gate, quantum gate.
Right. So in quantum mechanics, if you perform reversible operations, by definitions, they have to be unitary. Yes. Gate operations are unitary. So that you have to do. But in the end, if you have to extract some information from the system, then there is no recourse to, you cannot just simply do anything reversible. As soon as you want some information of the system, you have to apply irreversible operations. And in those irreversible operations, there is a cost in terms of entropy, and the state that you used in the beginning, the coherence is destroyed either fully or partially. So as long as you can do any operation, fine. But whenever if you want to obtain some answer to your computation from your quantum computers, you have to perform irreversible operation. You cannot escape.
Yes. Okay, sir. Thank you.
Thank you. So I see Professor Panigrahi wants to ask.
Yeah, Archan, I have this rather simple question. So when you were talking about detection or, so you are, suppose I'm assuming that these are all done through photons. So you are assuming loophole-free detection, loophole-free tests. Your quantum entanglement, all those testing are done, without any loopholes, right?
Yes. So actually, exactly, if we go back to, sorry, let me, can I, exactly. So that is the point I actually rushed through. So for example, in this one-sided device-independent test that was done experimentally, achieved experimentally in this work by the Chinese group. So these are, the two loopholes have to be, the two famous loopholes. One is the detection loophole, another is the locality loophole. So the detection loophole is bypassed, or it is, we say that there is no detection loophole if the detector have more than 85% efficiency in bell violation. But we are not doing bell violation. We are actually observing steering. So for steering, 50% detector efficiency is able to take care of this detection loophole. Now the second loophole has to do with this locality loophole, and in order to close this locality loophole, we have to show that there is no signaling between Alice and Bob. But again, this is a one-way, steering is a one-way protocol. So here we only need to show that there is no signaling from Alice to Bob's side. So that is actually ensured by local no signaling constraints. That is, the local marginal probabilities of Bob are independent of Alice's measurement settings. So Alice cannot signal to Bob by her choice of the input, and mathematically it is just described by simulations, and these probabilities are actually computed in the experiment as part of the experiment, and indeed we are able to show using various forms of the state, like for example here and here, that the state parameters given by A is nothing but theta, that is the non-maximally entangled state parameter, that indeed such no signaling constraints are satisfied in this experiment. So the locality loophole is also closed. So this is one.
Thank you so much. Very nice experiment. Beautiful.
Thank you.
Yeah. Are there any more questions? Otherwise, I'll ask one. I don't see any raised hands. So, coming to the Leggett-Garg inequalities, this generally one can also measure K3 and higher order correlations. So K4 is just chosen so that it matches the Bell kind of relation. Is that the?
Yeah. So this is an interesting question. So actually K4 is the original Leggett-Garg one. And of course, this is for this beers.
The minimum one needs is the K3. Right?
Yeah. Right. So this beer resembles to the Bell CHS mathematically. But
that's why this is.
Physics here is completely different. So we are
definitely
temporal correlation to it. Now, so this particular implementation was done using K4, but you could also ask the question: can we achieve implementation using other forms of Bell CHS? So that is a good question. And in this work, we did not go in that direction, but you could ask this question. So what is the optimum form of the Leggett-Garg or K3, K4 or higher temporal, which is easier to implement and which gives you the best result, given various assumptions. So that is one direction in which this work could definitely be extended. So that is
experimentally accessible. Which parameter would be more easily experimentally?
Yeah. So this one could actually indeed go on, so on and so forth. So that is an interesting question. But also I would like to point out that in the second work where we are testing this arbitrary D outcome measurement. So here again there is a choice, as you can see that this form does not resemble K4. So we have gone beyond that. So we have defined such a kind of correlation. But again, these are Fourier transformed condition probabilities. So what we find in this work is this what we define as tau2. So this is the minimum sort of resources we need to certify D outcome measurements. But again, you could ask experimentally. So this is a theoretical proposal. Experimentally, is this the most optimal, or do we need to go beyond that, or there is something more? So this is some interesting direction which one could look into. Thank you for asking.
Yeah, I see. That's a great question, Archan.
Yeah,
so you can see here anti-correlators, anti-commuting object. Right?
Yes.
Suppose that means, does it really mean that you are, because Pauli matrix anti-commutator will give rise to another one? Actually, measurement-wise, you are doing a single measurement, or both the operators have been measured?
No, you see, at the moment, we are talking of these individual measurements at various times. Okay. So these are 4 times, I think.
Oh, these are various times, huh? Okay, got it.
Yeah, these are real time, different time.
Very nice.
These are different times. Yeah, but what you're saying, Prashanta, can also be viewed from, if we take an analog to the spatial scenario. So then we could ask a similar question. So suppose we do an anti-commutator. So then, I mean, will that help us in order to answer some of these questions like self-testing, in that case using entanglement? So that could be, it could be thought of in that. That could also,
Also, there is another question. Generally, when we look at LGI, there is this non-invasive measurability, and there are these 2 assumptions. But this NSIT comes in later, right? It's like something which is additional, which would give a loophole-free measurement of this thing. Here, the way you have connected these 2, this is interesting, because you are saying predictability and no signaling in time together implies LGI. So could you please elaborate a bit on this?
Yeah, sure. So this is again a good question. So the original derivation of Leggett-Garg was based on non-invasive measurement and macrorealism. But later on, okay, so this formalism was not proposed by us. Again, there were other workers before. So what they stated in later works is that, so this kind of formulation Leggett-Garg was experimentally tested earlier also. But what some other people later they came in is to define another formalism which is easier to actually test in experiment. For example, if you base your arguments on the original framework of Leggett-Garg, you cannot really distinguish experimentally which is getting violated, either non-invasive measurement or realism. It is difficult.
One cannot say for sure, yes.
But if you base your argument on this alternative formulation, that is based on predictability and no signaling time, if you can take this together, then what you end up, if you take them together, you end up in the same mathematical framework or mathematical form of Leggett-Garg inequality. Okay, temporal correlation. So now if you perform some experiment in which you see that there is violation of your correlation, K4 or K5 or whatever, then you can say that one of them is violated. That is either predictability or no signaling time. Now the next question comes. Suppose you supply your state, a particular form of a quantum state, from which you can say with certainty that NSIT has to be violated. Then you end up with that is NSIT is violated. But if you go a bit further, the trick that we did employed in this work, we supplied a maximally mixed state, 1 by D, right? So we can see that for a maximally mixed state, NSIT is satisfied, right? Because you can satisfy yourself that it is the maximally mixed state. So whatever Alice does, the first round of Alice will not influence the second round of Alice, right? So in this case, we can say with certainty that predictability is violated. And when we say that predictability is violated, then we must be in the quantum regime. So because in classical regime, you cannot obtain such violation. And so with the use of this predictability violation, we can definitely guarantee quantumness of these measurement operators, or in other words, we can certify quantumness of the outcome measure. So this is the sort of trick or extension of the formalism, right? But if you want to see, I mean, which paper which was proposed this kind of Leggett-Garg formulation, I can send you the reference. It is also available in our paper here. That both these.
I see.
Thanks.
Okay. Thanks. Are there any more questions? I don't see any. Okay, if not, then let's thank Professor Archan Majumdar for this very nice talk. And over